Hi everyone, welcome back. This is Debasattam and you're watching the 10th lecture of EE635 Applied Linear Algebra. This is the second module. So in the first module, we saw that this, um, our very well-known um construction of Fourier series expansion of periodic functions can actually be viewed as best approximation, which is to say orthogonal projection of the given function viewed as a vector onto the subspace spanned by these special orthogonal basis vectors, namely the Fourier basis vectors, which are e to the power I 2 pi by capital T into small t, where capital T is the period, yeah, uh, and various multiples of that, yeah. Now, so this is all very good, but this but what is the benefit of looking at this, this Fourier series, or in fact Fourier transform also with some extension? What is the benefit that we get out of viewing this Fourier series as an orthogonal projection? The perhaps the most important benefit is that this point of view of looking at Fourier series as orthogonal projection um, tells us that there is nothing special about this Fourier basis vectors. It's just that in Fourier series, such a basis vector, such an orthogonal basis vector is already given to us. Yeah. But what if we ourselves construct our orthogonal basis vectors? Yeah. And then with that, it may be possible that we choose only those basis vectors which are important for us, which hold important information for us, and we can neglect all the other basis vectors, yeah, so that we can just look at, so for a very complicated function in an infinite dimensional function space, we may choose a finite collection of basis vectors which are important for us, and we just obtain the best possible approximation of the given function onto this subspace spanned by important vectors, yeah, and then treat that projection as the data itself, as a representative of the original data, original function. You may ask that what could be this important for us? What we mean by important? Well, for example, this importance could be resolution. Yeah. So let me try and explain. For that, I will need to share my screen. Right. Okay, so let us look at this situation. Yeah. So let me try and explain what I mean by obtaining various different basis vectors. Yeah. Like, for example, think of this set of polynomials in the variable x. Polynomials can also be viewed as functions, right? Like, for example, I take a function and take a polynomial f in Rx, then of course, if x is a real number for all x being a real number, isn't it? So this f could be a0 plus a1x plus dot 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 up to a n x to the power n. Yeah, now just put values for x, that will give you a real number. So you can view this as a function. So there, that means in Rx I can put this idea. So Rx admits a definition of inner product like two polynomials f and g. I can define the inner product to be integration 0 to 1. Notice that these polynomials may not be integrable over the whole of R. That means this integration from minus infinity to plus infinity for these functions may not converge, but this certainly does. two polynomials, taking the integration like this. This is a legitimate definition of an inner product. Yeah, just check that. So this goes to you as an immediate attention problem. Check, right, that this is indeed. So what you will have to check is something like what happens when f is equal to 0. Does this imply that f is also the 0 polynomial? Check. Yeah. Now it will turn out to be an inner product, and with this inner product, now you see I can try and ask this question, that suppose I have this standard basis for the polynomial, say 1x squared plus dot 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 up to x to the power some, give me any number, say capital N. Yeah, this span, the span of this is the so called R in x, right? This is the set of all polynomials, the set of all polynomials with degree less than or equal to capital N. So, and this is in fact a basis for that. Now you see 1x square up to x to the n, well, these vectors, these functions, they are not orthogonal. Yeah, indeed, look at 1 and x. If you integrate over 0 to 1 dx, this is x squared by 2, 0 and 1. This happens to be half minus 0. This is indeed half. Yeah. So 1 and x are not orthogonal to each other. Neither is x and x squared or 1 and x squared. No, these functions or these vectors are not orthogonal to each other. But then with the idea of this inner product and the idea of Gram-Schmidt orthogonalization, I should be able to orthogonalize these vectors. Now Gram-Schmidt orthogonalization will allow us, will imply existence of functions f0, f1, these polynomial functions up to fn, such that the span of 1 must be span of f0, which actually tells us that f0 has to be equal to 1. Then all degree 1 or less polynomials should be expressible as a linear combination of f1 and f0 and f1. Yeah, all polynomials of degree less than or equal to 2 can be expressible as a linear combination of f0, f1, f2, and so on up to 1x squared x to the power n should be expressible as a linear combination of f0, f1, f2 dot 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 up to fn. And not only that, these functions f0 up to f1, fn will be such that fi, fj integral 0 to 1 dx will be equal to 0. We should be able to figure out these functions equal to 0 for all I not equal to j, and will be equal to something, some non-zero constant when I is equal to j. If you want orthonormal, then this will have to be equal to 1 when you want orthonormality. But Gram-Schmidt orthogonalization will tell us that. So in fact, you see, now we have the idea of orthogonal polynomials. Yeah. Yeah. So then in that case, if somebody gives me a polynomial, so suppose f is an arbitrary polynomial now, yeah, then the best approximation of, by the way, okay, the best approximation of a polynomial f as a degree n or less polynomial would then be given by f hat summation k going from 0 to capital N, inner product f with fk divided by fk norm squared into fk, where fk are these orthogonal orthogonal vectors, orthogonal polynomials. It goes to you as a homework to construct these orthogonal polynomials. Find out what these polynomials are called. They have a very nice name. These polynomials are called. And then the second part of the homework, you will have to explain in words what is the physical meaning of the best approximation in this case. Yeah, is it all right? Okay. So such a best approximation, in this case in terms of degree, for that can be viewed as if, suppose the degree is the important information for me. So as the degree increases, my my importance to the polynomial decreases, in the sense that I want the best, I want smaller degree approximation, right? So that, with that, it means that I can do some sort of data compression here, right? Like, for example, suppose the original function f requires, say, 1,000 such basis functions to express. Yeah, but I'm interested only, say, components till up to degree 100. Yeah, originally the polynomial has degree 1,000, but I'm interested only in the degree 100 or less portion, the best approximation by a degree 100 polynomial. I'm interested only in that. So the best approximation in that case would give me the best possible representation of the original function, which requires 1,000 coefficients by 100 or less number of coefficients. So that way I save in the data. What is the price that I pay? The price that I pay is that all those other 900 data points, that data I'm missing. But I'm compensating for that in the sense that I'm because anyway I was not interested in that. This kind of seems a little artificial, that I'm not interested in the higher degree polynomials, and I can afford to lose that data. That seems kind of artificial, kind of, I'm trying forcefully to make sense of, give importance to what I'm saying. But that's not the case always. Let us try and see this particular thing. Okay. For example, think of, so what we are trying to discuss now is, from this point of view, the idea of a lossy data compression. So for example, suppose, once again, let us look at a finite period of time. I'm not saying that the function is periodic, but suppose there is some function which is described in this interval 0 to t. Yeah. What I can do here is I can first say, okay, let me try and find out the average value of this function. Yeah, then I will say that what is the component, how much variation does it have as far as, in the, as far as this is concerned, like say this will give me kind of a first variation. Then I may also try and see what is going on as far as variations like this are concerned. Yeah. What does this signify? It signifies that if I now try and see these green, red, and yellow functions, so the green one, the red one, and the yellow one, if I try and look at these are such that they give us information at various resolution level. This is, the green one is the coarsest, red one is mid-range, and yellow one in this particular case is the finest. So if there is a function which is 1 times the yellow function, then it varies like this. It varies quite quickly. It is high frequency. Whereas this red one is a little less frequency, and the green one is 0 frequency. Right? And now suppose I have a whole collection of these functions. I parameterize these functions and I collect them. Yeah, I have a whole collection of such functions which we are calling, let's say, phi naught, phi 1, phi 2, and so on, up to, let's say, phi capital N. Yeah, we can go ahead and check that these functions are already orthogonal. In fact, one can make them orthonormal. Yeah, and then, so because it's an orthonormal function, given an arbitrary function f here, I can just find out f check or f hat its approximation by doing the following, by summing them up, k going from 0 to capital N, dot product f with phi k divided by phi k norm square, which is just 1, into phi k. Right? Yeah, this would be the best approximation. And then I notice that as I increase this number n, I'm having the frequency or the variation is increasing. So when n is very high, then the function is like this. Yeah, it's a pulse width which very quickly varies. That's the most, that's a finer function. So if there is a function, so in this approximation, so now notice the following. When I'm doing this approximation business, if hat, these coefficients tell me how much weightage does weightages do these functions have, each of them. So if this k is for a very high k, this weightage is also high. That means for that particular frequency, for that particular resolution, I have this much weightage. The function has this much weightage for this much resolution. Right? Now, if it so happens that I don't want very high resolution, there is a threshold of resolution. Suppose there is a threshold of resolution in which we are interested. Why could that be? Why should that be the situation? Like, for example, very high resolution means very high contrast. So if we are thinking in terms of an image here, then very high resolution means very high contrast. So if this is your image, then you can view this as, some pixels. The highest resolution would mean that there is variation in between every 2 pixels, every nearby pixels, there is a variation. Right? So if So such a variation would in fact appear to be kind of no pattern for us, kind of would appear like a random signal to us, and we may not even be interested in that. I mean, our human eyes may not even view that as a picture, as an image, as an important information, because if it's random, then there is no information whatsoever, right? No meaningful information. Although from information theory point of view, randomness and information has a different connection. But anyways, we're not going into that realm. Yeah. So high frequency means high contrast, means very high resolution, and we may not be interested in very high resolution picture, right? So therefore, we might be interested only in the first, let's say, 100 of these basis vectors. Yeah. So somebody gives me an f, which is, so somebody gives me an f which is such that this is 0 and t. For every point here, suppose there are, let's say, this is sample, suppose there are 10,000 sample points, then 10,000 pixels. Yeah. For each of those pixel points or data points, I have this data value, which is like a huge storage. Yeah, if I want to store the data just as it is, like this one, for every point, for every sample point, store the value, then it would require, let's say, 10,000 unit of memory. Yeah. If I store only the first 100, that may not give me meaningful information. That may give me something like, yeah, this much. Or if I sort of randomly space out these 100 points and store them, that also may not give me all the information. So I have to be cleverer. So instead, what I do is I look at this f, and then I look at its best approximation f hat in terms of the f hat in the span of the first 50 up to 500 functions. Yeah, 599, let's say, because I want because I'm counting from 0, 599. Yeah, that gives me the best approximation in terms of this resolution. All the higher would be higher resolutions, and those higher resolutions are such that, let's say, our human eye is not even able to make any differentiation between something that has that has something which cannot discern the functions for 500 or higher. Yeah. In that situation, I in fact have to store only 100 points, 100 values. In what sense? Because their f hat will be this, alpha 0 into phi 0 plus alpha 1 into phi 1 plus dot 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 up to alpha 99 to phi 99, which means I now have to store only these alpha data, only 100 data points. But it's a lossy compression, but it's not bad because I have done my best to do this approximation. This is not some random, like only the first 100 or 100 randomly placed points, not like that. I have done it with resolution idea. So I have the coarsest resolution. If I want finer and finer resolution, I will have more information, but those informations anyway does not add much to my understanding. Right. So that is how this lossy compression is done. In fact, this, what I have expressed here, what I have tried to explain here, is what is known formally as a wavelet transformation. Wavelet transforms, right? This wavelet that I have discussed here is a special kind of a wavelet called the Haar wavelet. There are all sorts of other kinds of wavelets which are nothing but an orthonormal basis for the functions that we are interested in. So those wavelets will have their own properties. There will be their own notion of importance attached to those basis functions. They will be ordered like that, ordered in the order of importance. Okay, so the further down the line you go in the list of these wavelets, the lesser would be their importance. Yeah, so once again, one can talk about their the projection of a given function onto the first few of few wavelets of importance, and that would be its compression. This whole idea of doing data compression using wavelet transform is known as multi-resolution analysis. Yeah, data compression standards like JPEG uses such transformations to do the data compression for images. Okay, right? So this is what I wanted to discuss about lossy data compression. Now we're going to see whatever time we have left for the second module, we're going to see another very quick application of this very this amazing idea of best approximation in terms of orthogonal projection, namely the idea of what is known as a Wiener filter in estimation theory concerning random vectors. So in a nutshell, the problem is like this. We would like to estimate a random vector from observation of n random vectors. What I mean by that, suppose I have the information for x1, x2, dot 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 up to xn, and suppose so these are random variables, these are random vectors, so each of them is a random vector. I'm sure you know about random variables. When you have a multiple, n tuple of random variable, it's a random vector. So x1 is a random vector, x2 is a random vector. So each of these x1 up to xn, they take values in, let's say, Rn, R small n. Yeah, all of them take values in R small n. Yeah, is that all right? So they are random vectors. Now, for all you know, they can be random variables also, doesn't really matter. These random vectors, and somehow let's say I can have an observation on these guys. So there is some measuring device which can measure what is the outcome of these random variables. It can measure those outcomes somehow, right? And then suppose there is another random vector y which I want to predict, I want to estimate, to be estimated from those observations. Yeah. What could be a situation like this? Well, if you remember in the very first lecture, I had said that there is this fly which is flying within a room. Yeah, this might be its flight path, and there is someone here who is observing this fly with a binocular and measuring its whereabouts, and from there it would like to estimate. So it has measured these positions of the fly at various time instants. It would like to predict where this fly would be at the next instant. So these could be xn, xn minus 1, xn minus 2, and so on up to x1. And this could be y. This y is what we would like to predict. Yeah, this is just one example. You'll find a form of this this problem. You'll find this problem in various different forms in various situations, but all of them actually is the comes under the purview of that same general idea that we would like to estimate a random vector in terms of observations of n random vectors. What is to be done here? Well, perhaps the easiest solution here is the following. We first notice, so I'm going to give you the easiest solution. Many more different solutions, more difficult solutions are also possible. The easiest solution being, well, notice first that because they are random vectors, any linear combination of these random vectors also is a random vector. So it makes sense. I going from 1 to n, is a legitimate random vector, is also a random vector. What does that tell us? That tells us that, if I look at the span, so these are where alpha i's are real numbers. Yeah. So this span of x1 up to xn is a vector space. Yeah, is a real vector space. We are learning linear algebra, so there should be some benefit of learning linear algebra, right? And that is the fact that this is a vector space. Not just that, this vector space is also an inner product space. Yeah. Why is it an inner product space? Well, one can define an inner product here in terms of, okay, so suppose, what should I say? Suppose Z1 and Z2 both are in this span. It doesn't have to be in the span. In fact, suppose they are random vectors. Suppose Z1, Z2 are random vectors. Suppose Z1, Z2 both are random vectors of the same size. Yeah. Also, there is one more assumption that has to be made, is a random vector of zero mean. Okay, their mean is zero. All of them are zero mean. Then this linear combination also is zero mean. So these are all zero mean. So their linear combination also is zero mean. Yeah, zero mean is important for us. Otherwise, I cannot make it into an inner product space. Suppose Z1, Z2 are random vectors. Both are zero mean. That is, their expectation is zero. Then we can define, okay, how do I define the inner product? Inner product of Z1, Z2 by definition is expected value of Z1 transpose Z2. Yeah, this is it. This is an inner product. One can verify that this indeed is an inner product. Okay, because ultimately it's going to be some integration. No, it's going to be integration of Z1 transpose. There will be an f Z1 function, which is the density function for Z1. There will be a function of these will be matrices. I mean, for let me just do it for random variables. You can understand what will happen for random vectors. It's going to be Z1 f Z1 f Z2 Z2 dx or d xi, whatever, d xi, right? So this in fact basically is an integration, and therefore just you can check that this is going to be an inner product. Okay, and because it's an inner product, I can talk about orthogonal projection, which means the best. Okay, so it's an inner product space, and then it's a vector space. So for this y, I can do this estimation, right? That y hat, suppose, is defined to be alpha 1 x1 plus dot 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 up to alpha n xn, where alpha 1 up to alpha n are unknown real numbers. My estimator would give me these numbers, so that this is the best possible approximation. Now, how do I get that this is the best possible approximation? Well, because it's in inner product space, there is a norm. So best approximation here would mean minimum value for y minus y hat, the norm squared. But what is this? This would be expected value of y minus y hat transpose y minus y hat, isn't it? So, but this is a complicated expression. This is an expectation, right? This is not just transpose of two vectors. You have to do this transpose of two vectors. There should be a something in between sitting here, and then you have to carry out this integration. It's going to be a really difficult thing. However, an integration over how many variables? N variables, because because it's an n dimensional vector. So it's a multiple integral that it's a multiple integral that you're going to perform. That may not be very easy. But then, because it's an inner product space, this length has been derived from the inner product. All the theory that we have learned about inner product spaces and best approximations on inner product spaces, or rather in inner product spaces, would be applicable here, which means y hat is a best approximation if and only if the error vector y minus y hat is orthogonal to x1 dot 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 up to xn, all of these basis vectors, right? Now, what does that mean? Well, that means expected value of y minus y hat, the transpose, into xi must be 0. What is that? That is expected value of y transpose minus alpha 1 x1 transpose xi minus alpha 2 x2 transpose xi minus dot 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 minus alpha n xn transpose xi. That is ought to be 0. Yeah. There is an xi here also, right? Yes. Expectation is a linear operator, which tells us that this is nothing but, so if I rearrange this equation, what I'm going to get is, yeah, expectation of x1 transpose xi into alpha 1 plus dot 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 up to expectation of xn transpose xi into alpha n. That ought to be equal to expectation of y transpose xi, and this ought to be true for all I. So this gives me an equation. This is the ith equation. That way I have n equations, capital N number of equations, which can be written in the matrix vector form as expectation of x1 transpose x1, expectation of x1 transpose x2 dot 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 up to expectation of x. Did I make a mistake? Yeah, I think I did make a mistake. It's not like that. It is x2 transpose x1. Yeah, this is xn transpose x1. This is expectation of x1 transpose x2. This is expectation of x2 transpose x2 dot 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 expectation of xn transpose x2, so on. Expectation of x1 transpose xn, expectation of x2 transpose xn, expectation of xn transpose xn. This multiplying alpha 1 up to alpha n must be equal to the vector obtained by expectation of y transpose x1 dot 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 up to expectation of y transpose xn. Yeah, is it all right? this matrix out here is obtainable from the statistics, so from the known statistics of the of the of these random variables. This also is a part of this of the known statistics, so I know these expected values, and from there I just have to solve this linear system of equations to obtain this alpha 1 up to alpha n. Yeah, that's it. Now one may ask that uh, why is this orthogonal projection so difficult here as opposed to the other orthogonal projections that we have seen so far, namely the Fourier series and the wavelet transform and so on. The reason being, these x1 up to xn, these observation random vectors, need not necessarily be orthogonal to each other. That is not an orthonormal basis. You see, it's just some observation. I have no handle on that. These observations are coming to me, and that's why I don't know whether these random variables are orthonormal or not. If they're orthonormal, however, then their dot products will be zero, no? You see, in that situation, all these entries will be zero. Let me explain. The random variable xi, xj orthogonality by definition means their inner product is zero, which is xi transpose xj expected value is zero. If that is so, then this matrix out here, no, this matrix turns out to have all off diagonal entries to be zero. Only diagonal entries are there, so it's a diagonal matrix. And if it's a diagonal matrix, then it's very easy to invert, isn't it? Yeah, these x1 transpose x1, they are the so-called autocorrelation or autocovariance. They are the same here because they all of them have been assumed to be zero mean. So these autocovariances, they are non-zero because of non-zero random variables. These non-zero autocovariances lie in the diagonal, and in the diagonal, uh, and if they're orthogonal, these random vectors, if they are orthogonal to each other, then it's a diagonal matrix, and one can easily invert this and obtain alpha 1 up to alpha n. And in that case, you can notice that when you invert, the formula is just the formula for the projection, namely the dot product, that is cross correlation between y and xi's divided by the norm squared of xi's, the standard formula for the projection. Yeah, because x1 up to xn in general need not be orthogonal, that's why I have to solve this equation. But then what people have noticed, what in fact Wiener had noticed long back, 1960s if I'm not mistaken, or perhaps earlier than that, is the fact that even though these are not orthogonal to each other, one can do Gram-Schmidt, no, and make them orthogonal. So instead of having x1 up to xn, yeah, change the observations so that you have x1, what should I call it, x1 prime dot 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 up to xn prime. It's a new basis which is orthogonal by doing Gram-Schmidt one after the other. First, x1 and x1 prime have to be, you know, scalars of scalar multiples of each other, because I don't want orthonormal. I can just take x1 to be equal to x1 prime. Then when x2 arrives, I will, instead of taking x2, I will take projection of x2 onto x1 from the span of x1, look at the error, and that I will call as x2 prime. That is how I'll take x1 prime and x2 prime. When x3 arrives, I will project x3 onto x1 prime, x2 prime, look at the error, that I will take at x3 as x3 prime. So that is how I will take my observations. This changing of a given set of observations to orthogonal observations is called whitening, or whitening of the sequence, because making them orthogonal to each other is what it, you know, the technical term for that is, you know, you're making it white, you're making them uncorrelated. Yeah, or in that case, this sequence of, you know, mutually orthogonal, mutually uncorrelated sequence is called an innovation sequence. These are some names. I mean, names are not important. The idea is, as Feynman had said long back. Yeah, but essentially they're all the same ideas. It's just that in different subjects they talk different, they are taught differently, they are given different meanings, they are given different names, but at the root all of these are exactly the same idea, starting from starting from Fourier transform, Fourier series, wavelet transform, and now this innovation sequence. All of them actually go back to the idea of Gram-Schmidt orthogonalization and best approximation by taking orthogonal projection. That's it. Okay, so let's put an end to this module. I hope you have learned something new here, some new applications. In the third module, we are not going to look at any applications anymore. We are going back to our abstract studies of inner product spaces, and we'll learn this idea called the orthogonal complement. Okay, so let's meet at the other side of this break. Till then, bye bye.